So welcome to the solution of day 16 Tuesday questions on digital electronics. And if you have seen the questions, then the questions were actually handwritten. And through this lecture or through this video solution, I want to explain you how the ripple carry adder works and how the gate delays are incorporated in the functioning of the ripple carry adder. Then we will look at carry look ahead adders, and then we'll look at serial adder and 2's complement addition and subtraction through a simple adder. Okay, so all these four are the topics of this video solution. So we will solve all these four very important topics for gate. Okay, and in all the topics we will try to incorporate gate delays, because gate delay is a very favorite topic of gate examiners, and this has to be analyzed thoroughly. So that's why I've kept these questions, and I will analyze all the questions, all the circuits, combinational logic circuits, using incorporating gate delays in them. Okay, so let's start with the first question. The first question was explain the working of the ripple carry adder and explain it using zero and non-zero gate delays. Okay, so first of all, we have to explain, we have to see what is ripple carry adder. Okay, now before moving to ripple carry adder, I will explain you the simple full adder. Okay, simple full adder. Now full adder means it is a block which has three inputs. Two inputs are A, B, and the third input is carry input. Okay, carry input. The output is the sum. There are two outputs, that is sum, and another output is carry output. Okay, so it is actually sum is equal to A plus B plus C in, and if any carry is generated, C out is equal to 1, otherwise it is 0. Okay, so for example, since there are three inputs A, B and C in, so obviously there are 8 possibilities. Okay, we know all these 8 possibilities. The output are sum bit and the carry output bit. Okay, so 0 plus 0, 0 plus 0 plus 0 is 0 and no carry. 0 plus 0 plus 1 is 1 and there is no carry. 0, 1, 0, there is 1 and no carry. 0 plus 1 plus 1, as we know, 0 plus 1 plus 1 is 0 with 1 carry. Okay, because 0 plus 1 is equals to 1 0, that is 2. Okay, so this is sum bit and this is 1 carry bit. So 0 and 1 carry. Again 1 0 0, it is 1 with no carry. 1 0 1, it is 0 with 1 carry. 1 1 0, it is 0 with 1 carry. 1 1 1, as we know, 1 plus 1 plus 1 is 3. 1 1, so this is sum bit and this is carry bit. So 1 and 1. Okay, now from here we can see that sum is equal to A XOR B XOR C, and carry bit is equal to, there are 4 terms, these 4 terms are there, so we can see that it is equal to, so if we see this, then it is actually equal to A bar B C plus, if we look at it here, then it is A B bar C. Here we will have A B C bar, and the last one is A, B, C. Okay. Now we can see that if we take AB as common here, we'll get C out is equal to AB plus, if we take C as common here, C A XOR B. So this is your C out expression and this is your sum expression. Okay. Okay. Now there are many methods to actually design this full adder. The basics is okay. Now very important thing is there are many. So I'm writing it. There are many ways to design a full adder. Okay. Now the design that you will choose will be according to the details given in the question. So for example, if in a question, it is given that all gates are available, all gates are available. Okay, there is no restriction. Okay, all gates are available and design full adder with minimum delay. Okay, with minimum delay. Now in this case we can see that for example, if we have a 3-input XOR gate, okay, a 3-input XOR gate, A, B and C are given as input. Okay, so there is no restriction given to us. It is given that all gates are available. So here we can see that A XOR B XOR C, that is a sum, we can get it in one gate delay only, because we have used only single gate here. Only one gate delay is needed. Now we know that C out is, as we can see that C out is equals to, since A, B, C in are the inputs, so 3, 5, 6 and 7. When the inputs value is 3, 5, 6 and 7, C out is equals to 1. So if we simplify this, then we can see that it is equal to A, B, C in 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 3, 2, 4, 5, 7 and 6. So it is 1, 1, 1 and 1. So this is 1 K-map. If we reduce it, so we will get 3 squares like this. So we can see that C out is equals to B C in plus A B plus A C in. Okay, so this square is B into C in, this is A into B, and this is A into C in. Okay, so this is your C out. So here we can easily see that we need 3 AND gates and 1 OR gate. So AB, BC in and AC in. So 2 level gates are needed here. Okay, so 2 gate delays are needed here. Okay, so if we have a full adder and in the question it is given that all the gates are available, there is no restriction. So in that case, the sum bit has 1 gate delay and the carry bit has 2 gate delays. Okay, so now let's move on to the next case, that is case 2, second case. Now the second case is, here if in the question it is given that we have half adders given to us and we want to design the full adder using half adders. Okay, now first of all let me explain you half adders also. So what is half adder? Half adder has only two inputs A and B. There is no carry input available. Okay, so only two inputs are there. Half adder, A and B, C out and sum. Okay, so A and B are available. C out. Okay, first I will write sum and then C out. So that's very simple. That 0 0 is there, output is also 0 and 0. 0 1, sum bit is 1, carry is 0. 1 0, sum bit is 1, carry is 0. And when both 1 and 1 are both A and B are 1, then we know that output is 1 0. That is carry is 1 and sum is 0. Okay, so here we can see that sum is equals to A XOR B. Okay, and carry is equals to A into B. Okay, so suppose we want to design a full adder using two half adders. Okay, so in this case the design is like this. Okay, the design is like this. We have a half adder where two inputs A and B are given. So we know that the sum output is equals to A XOR B and the carry output is A into B. Okay, the third input C. Okay, and the second half adder is here, half adder. We know that the output we want of the full adder, the output is A XOR B XOR C. So we will apply this as one input to the half adder and C as another input to the half adder. So output will be the XOR of the two inputs, that is A XOR B XOR C. Okay, and as we know that this is some output and the carry output will be, and the carry output we know that from the half adder is equals to the AND product or the AND of the two inputs, that is A XOR B into C, that is the second output. Now we know that the carry output is equals to, as we know that the carry output of the full adder equals to A into B plus C into A XOR B. So we have A into B here and C into A XOR B here. So we will OR these two and we'll get the C output here. Okay, so we can easily see that to design a full adder, we need two half adders and one OR gate. Okay, one OR gate. Okay, now if we want to, okay, so I have to add one more page here. If we want to analyze the gate delays here, okay, so let us assume that half adder has delay to produce sum is equals to TS and carry is equals to TC. Okay, so let us assume that at t equals to 0 we applied the inputs A, B and C. Okay, so after TS seconds we will get this output here. After TC seconds we will get this output here. Okay, now if you look at the second half adder, this input is available at t equals to 0 time instant and this input is available at TS time instant. Okay, so the output that will be produced, the sum output that will be produced here will be, okay, so since this is available at TS, this is available at 0, so we will take that the inputs are available at TS time instant only. So this half adder is actually producing the output sum after TS time delay. So this output will be available at 2s time instants only, and this output will be available at ts plus tc time instant. Okay, because the inputs are available at ts time instants, and to produce the carry it takes tc time instants. Okay, so ts plus tc time instants to produce this at the output. Now this is available at the input of the OR gate. Okay, now here we can easily see that this input is available at tc. Now this is available at ts plus tc. So now as we can see here that this input is available at tc, this input is available at ts plus tc. So we can say that both the inputs are available only at time instant ts plus tc. Okay, and if this gate has a delay of to, that is t or gate delay, so the cout will be available only at ts plus tc plus to. Okay, okay, so the full adder will have some available only after 2 ts time instants and carry output only after ts plus tc plus to time instant. Okay, so this is the kind of question that they can ask. Okay, so half adder is given and they have given that the half adder has sum and carry delay this much and OR gate has this much delay. So find out the delay or to of the full adder to produce the output, and the output, that is sum and the carry bits. Okay, so this is one case. This is another case that we have seen that all the gates are available. Okay, so this is there. Okay, one more thing that we can have, one more case that we can have is example third. Just taking one more case. Suppose it is given that inputs are available in non-complemented form only. Non-complemented form only, and all gates with two inputs are available. Okay, so only two input gates are available. There is no three input gate. So what is the delay in full adder? Okay, so we know that the sum is equals to a XOR b XOR c. So we will use two input XOR gates, that is a, b and c. So we need two 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 input XOR gate, and we can see that there are two levels. Okay, now if you are not able to understand the levels, I have explained them in the previous Tuesday digital electronics video solutions. Okay, so just I am telling you the gates in which the inputs are directly connected are called level 1 gates, and the gates to which the output of level 1 gates are connected is called level 2 gates. Okay, so this is level 1 gate, this is level 2 gate. So there are two levels, so there are two gate delays here. Okay, now I think I have to pay. Okay, now so to produce the sum bit we need two gate delays, and now to produce the carry bit, since only two input gates are available, so first of all let's write C out. What was C out? Okay, so we know that what C out is actually um, let me first of all let's see. So C out is actually A, B, C are the inputs, and C out is 1 when it is when the input is 3, 5, 6, 7. Okay, so let's minimize the expression of C out. So it is A, B, C in 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. It is 0, 1, 3, 2, 4, 5, 7, 6. So 3, 5, 7 and 6. Okay, so this is one combination, that is C out is equals to 1 square is this K map minimization, it is BCN plus another one is this A into B plus another one is this. Okay, so it is again A into Cn. Okay, so these three combinations are there, and now we can see that since, okay, so easily we can see that it is AB, it is BCN, it is ACN. Okay, so this is your C out. So we can see that this is level 1 gate and this is level 2 gate. So C out has also 2 gate delays. Okay, and there is no need of any complemented, there is no need of any complemented input. Okay, so this is the so when all the gates are available and only two input gates are available, so we can see that sum has 2 gate delays and carry also has 2 gate delays. Okay, so full adder has 2 gate delays to produce the output sum and the carry output. Okay, so now let's move on to the implementation of the full adder using, if the question is like you have only NAND gates available and you have to implement the full adder, so what is the delay? So let's look at it. Full adder using NAND gates. Okay, now in the previous lecture of the digital electronics we have seen how to implement a XOR gate using NAND gates. Okay, so we know that 4 gates are needed, 1, 2, 3 and 4, to produce the XOR of two inputs A and B. So this is A XOR B. Okay, and this is your carry in. Okay, so carry in is so this is another, so 1 2 3 4 are designing one XOR gate, 5 6 7 and 8 are designing another XOR gate. Okay, so two XOR gate connected in series will produce the output sum, that is A XOR B XOR Cn. Okay, so these four and these four are designing the XOR gate, and here we are getting the carry output bit. Okay, so we can see that there are 9 gates needed, 9 NAND gates needed, and if we look at the levels, so this is level 1 because directly inputs are connected, this is level 2, level 1, level 2, level 3, level 4, level 5 and level 6. So there are 6 levels of gate, so we can say that the output, that is sum and carry bits, need 6 NAND gates delay. So these are very important because these things come handy when such questions came in gate exam. Okay, it is very difficult to design the at that time. So if you have read these things 1 or 2 times, then it is very easy for you to solve in the gate exam. So when NAND gates are needed, only NAND gates are available. So 9 NAND gates are needed and 6 NAND gate delay is required for producing the output from the input. So if we have only NOR gates available, if only NOR gates are available, okay, now as we know that in NOR we need 5 NOR gates to design an XOR gate. So that is what happening here. Okay, so we have seen a different design in the previous case, in the previous class. So this is 1 2 3 4 and 5, these are designing one XOR gate. 6 7 8 9 and 10, these are designing second XOR gate. So one XOR gate, second XOR gate in series, we will get the sum bit at the output, that is A XOR B XOR Cin. Okay, and so now let's look at the design first. Okay, so here we will get, so let me zoom in, A plus B conjugate. Here we will get A conjugate, here we will get B conjugate, and here we will get A conjugate plus B conjugate whole conjugate. That is equal to A into B, and A plus B conjugate is equals to A conjugate B conjugate. So they both are getting added here. So here we will get AB plus A conjugate B conjugate whole conjugate. Okay, so this expression is XNOR, and XNOR inverse is XOR. So we are getting XOR here, no issues. Okay, now so here Cin is there, so we will get Cin conjugate here. Okay, A plus A XOR B is here, so here we will have A XOR B conjugate. Here we will get A XOR B conjugate plus Cin conjugate whole conjugate. Okay, so if we write it, then we will get Cin multiplied by A XOR B. Okay, now as we know that x plus y whole conjugate is equals to x conjugate y conjugate. Okay, we know these properties. Okay, so that is property I am applying. So I'm just trying to prove that this is C out. Okay, there is no issue that this is sum because there are two XOR gate connected in series. So here we have A into B as it is coming from here. So here we have Cin into A plus A conjugate B. Sorry. Here we have Cin multiplied by A XOR B. Here we have A into B. So here we will get AB plus A XOR B into Cin whole conjugate, and this is working as a NOT gate, so we'll get C out here. So this is the design. I don't think you have to remember all this. The only important thing is here we need 12 XNOR gates. Sorry, NOR gates. Here we need 12 NOR gates to design the full adder. Okay. Now if we look at the levels, so this is level 1, this is at level 2, this is level 3, this is level 4, 5, 6, 7, 8, 9. So 9 levels. So we have 9 NOR gate delays. Okay, but generally NOR is not used or asked in gate exams or any exams. NAND is more important. Okay, so just try to remember how this full adder is being implemented or designed using NAND. Okay, so we have seen 4 cases. In the first case, we designed using all the gates available. In the second case, we designed using half adders. In the third case, we designed using the gates of only 2 inputs. In the fourth case, we designed using NAND only. In the fifth case, we designed using NOR gates only. Okay, so these cases are important. They can ask you a question related to this. Okay, now let us. So we have one full adder available to us. So now let's look at what is ripple carry adder or ripple adder. Okay, it is a simple addition mechanism. For example, I want to add two numbers and both the numbers are of 4 bits. So A3, so there are 4 bits, right? So A2, A1, A0, B0, B1, B2, B3. So I want to add these two numbers. So there are two numbers each of 4 bits. So how do we do addition? First of all, I will add A0 and B0. Okay, so this is the method. First of all, I will add these two. I will write the sum bit here. Okay, and the carry that will be generated will be given to the next case or the next numbers. So then I will add the carry A1 and B1, and then I will get a sum bit, that is S1, and a carry that will be transferred to the next level. Carry A2 and B2 will be added to produce S2, and again a carry will be generated. That carry is added with A3 and B3, and we get S3, and a carry is generated, that is C out. So this is the output, and this is how the ripple carry adder or ripple adder works. Okay, now it's very simple that first of all we need an adder that will add A0 and B0, produce a sum bit and a carry bit. That carry bit is transferred to the full adder of the next level, and the full adder of the next level has two inputs A1 and B1, and Cin is the output carry of the 0th level. Okay, now at the second level we have A2 and B2 are the inputs to the full adder, and the carry output of the first level is actually applied as input to the full adder of the second level. Okay, and so on. Okay, so this is the case. Okay, now I have used four full adders. Okay, four full adders. But important point here is that since there is no input, since there is no carry input at 0th level, we can use, we can use a half adder at the 0th level also. Okay, there is no need of full adder because there is no carry input here. Okay, so if we are using a full adder, then also we have to ground this carry input. Okay, or we can use a simple half adder at the 0th level. So it's very simple that the 0th bits of A and B inputs are applied. Okay, the sum bit is the S0 of the result, and the carry output of this level is acting as an input carry to the next level. Okay, to the next level. Okay, so this is working as a Cin. A1 and B1 are the inputs, output is sum bit, and the carry bit or output of this full adder at the first level is acting as an input to the full adder of the second level, and the output of the carry output of the second level is working as an input carried of the third level, and this is C out, this is S3, S2 and S1. So this is how it is working. Okay, simple addition is actually implemented using a digital logic circuit. Now, what is the issue problem in this circuit? Now let us analyze the problem. Okay, now let us see assume that, let us assume that I have a full adder. Okay, I have a full adder with inputs A, B and C in, the output S and C out. This is full adder. So since gates have delay, so let us assume that there is a delay of TS and there is a delay of TC here. Okay, to produce the output from the inputs, TS is the delay for the sum bit and TC is the delay for the carry bit. Okay, now let us look at, suppose we have 4 bits input available. Okay, no need. Okay, so let us assume that only three bits are available. There is no issue. I will just explain it using 3 bits also. So the carry input of the FA0 full adder 0 is 0. A0 and B0 are connected. C out and S0. So this is connected as the input to the second one. As we know, C in A1, B1, full adder 1, S1, and the carry is connected to the out. Okay, so this is C2, full adder 3, full adder 2. Okay, now what's the problem? Let's look at it. Now, as we know that the inputs are available at all the inputs A1, B1, A2, B2, A0, B0 all are available at t equals to 0 seconds. They all are available at t equals to 0 seconds. Okay. Now, to produce the sum bit here, it will take ts seconds. And to produce the output C out here, it will take tc time seconds. Okay. Now, since this full adder is waiting for, it has three inputs. Okay, A1, B1 and Cn. Okay, A1, B1 are available at t equals to 0, but the Cn is available at tc time seconds. Okay, tc time. Okay, so this input is available at tc time. So the inputs are available to the full adder 1 only at tc time. Okay, now the sum bit will be produced at ts plus tc. The sum bit S1 will be produced at ts plus tc. This carry out will be available at 2tc. Okay, so we can see that the full adder second has inputs A2 and B2 available at t equals to 0, but the Cin is available at 2tc. Okay, so the output sum S2 will be available at 2tc plus ts, and the carry will be available at 3tc, or I can say that 2tc plus tc, that is 3tc. Okay, now when this is available applied to full adder 3, okay, so full adder 3 will produce the output at 3tc plus ts for the sum bit and 3tc plus tc for the carry bit. Okay, so we can see that because of delay in the gates, this ripple carry adder, since I have used only 4 bits, I am just adding two numbers of 4 bits. So we can see that the sum is available. So let us assume that if there are n bits, then the final, the last, so we will have n full adders in the circuit. Okay, so we can see that the full adder 0 will produce the carry output at tc, and this is at ts. Full adder 1 will produce the output sum bit at tc plus ts, and this at 2tc. Similarly, the last one, full adder n minus 1, will produce the output. So let me write for FA2 also, so that it is clear. 2tc plus ts, and it will be 3tc. So the carry bit will be produced at ntc, and the sum bit will be produced at n minus 1 tc plus ts. Okay, so we can see that the final output, the reliable output, will be available only when the last full adder produces the reliable output, and it is produced only at n minus 1 tc plus ts and ntc. Okay, so we can say that as the value of capital N increases, the delay of getting the reliable output from the ripple carry adder increases. So this is the problem of the ripple carry adder, and I explained you the ripple carry adder very thoroughly. Okay, so now you will be able to solve any gate question related to the ripple carry adder, because mostly the questions related to ripple carry adder will be related to gate delays only. Okay, now let's move on to how to solve this problem of ripple carry adder. Okay, so the solution is look ahead carry adder. Now let's look at look ahead carry adder. Okay, so we have seen the problem in ripple carry adder. The ripple carry adder has the problem that since the carry is propagated from one full adder to another full adder, so the full adder, so if you look at it here, so the second full adder has to wait for the full adder 0 to complete its working. Similarly, the full adder n minus 1 has to wait for the previous full adder to finish its working. Okay, because they are waiting for the carry input. Okay, so that problem is solved by look ahead carry adder. Okay, so let's look at the look at carry adder. Okay, now as we know that the formula of carry output is equals to A into B plus A XOR B into Cn. Okay, so C0 is the input carry. Okay, so in the previous case we have taken there is no carry input, so let us take that there is some carry input, and in the 0th place also we are using a full adder. Okay, so we are not grounding the C0. Okay, as we have done in the previous case, we are just taking the C0 is the input carry to the adder. So we can say that the carry output from the full adder 0 is C1. Okay, so C1 is equals to A0 B0 A0 XOR B0 into C0. So let us say that AI into BI is equals to GI. Okay, just for sake of simplicity, and AI XOR BI is equals to PI. Okay, so we can say that C1 is equals to G0 plus P0 C0. Now C1 is input to the full adder 1. The carry output from full adder 1 is C2. Okay, so we can say that C2 is equals to A1 B1 plus A1 XOR B1 into C1. So we can say that it is G1 plus P1 C1. Now C1 we can put it from here, so we will get G1 plus P1 G0 plus P1 P0 C0. That is your C2. Okay, now C2 is the carry output from the first full adder, and it is input to the second full adder. Okay, now the carry output from the second full adder, that is C3, will be equals to A2 B2 plus A2 XOR B2 into C2. So this is G2 plus P2 C2, and we can put C2 from here. We will get that is G2 plus P2 G1 plus P1 P2 G0 plus P1 sorry, P2 P1 P0 C0. Okay, this is your C3. Okay, similarly we can find C4, similarly we can find C5, and so on. Okay, so let me write C4 also. Okay, so this C3 is output, carry output from full adder 2. Okay, and it is input to full adder, it is input to full adder 3. Now carry output, output carry from full adder 4, sorry, full adder 3 is C4, that is equals to A3 B3, A3 XOR B3 into C3. So that is equals to G3 plus P3 into C3, we can put it from here. So we'll get P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C0. Okay, so we get C4 from this expression. Okay, so this is very important because the result that I'm just going to tell you is very important. Now let's look at the result. So I just shown only 3 carries here, C1, C2 and C3. Okay, now if we assume that we know that G0 is actually A0 into B0, P0 is A0 XOR B0, G1 is A1 into B1, P1 is A1 XOR B1, G2 is A2 into G2, sorry B2, and P2 is A2 XOR B2. So to produce C2, C3 and C1 carry, we only need 2 gate delays. Okay, 2 gate delays are needed from these P2, G2, P1, G1 and P0, G0 and C0. Okay, now let's look at how this whole adder will work. Okay, so this is very important result that only 2 gate delays are needed from these uh, P and G to get the carry outputs. Only 2 gate delays are needed. Okay, because these are at level 1 and these are at level 2 in the circuit. Now let's look at the whole adder. This is the whole adder. Okay, so these are the inputs. These are the inputs that are available. These all inputs are available at t equals to 0. These all are available at t equals to 0. Now there is one gate delay. Okay, there is only single gate delay because they all are at level 1. Single gate delay, single gate delay to generate all these pi and gi. Okay, to get all these pi and gi. Now from pi and gi we know that 2 gate delays are needed to produce these carry C4, C3, C2, C1 and as we have seen. Okay, now and from here to get the complete output, we can easily see that the output, the sum bit can be easily obtained by single gate delay. Okay, now if we want to analyze this whole thing, then we can first of all let's start from A0, B0 and C0. So these inputs are available at t equals to 0. Okay, after one gate delay we are getting all this P0, G0 and C0. Okay, and this S0 can easily be obtained. There's no issue in getting the S0 because C0 is already available, P0 is available after one gate delay, and after that we can get S0 after simple 2 gate delays. Okay, there is no issue in getting S0 because we can easily get it. But let's look at S1. Okay, now for S1 we need that. Okay, we have A1 B1. Now after one gate delay, P1 and G1 are available. So P1 is available after single gate delay, but C1 is not available. C1 is not available because for C1 we can, here we can see that for C1 we need that there are two gate delays from these inputs P0, P0, G0 and C0. Okay, so for C1 we need that there are two gate delays here. Okay, there are two gate delays from the inputs pi gi to get the carry output. So there are two gate delays, so this c1 is available after two gate delays, and thus the output s1 will get after by, so this pi and gi are available after single gate delay, c1 is available after two gate delays, and s1 will take one more gate delay. So the total delay here is four gate delays. Okay, four gate delays. Similarly, for c2 also we can see that for c2 we need two gate delays. So pi gi are available after one gate delay, c2 will be available after two gate delays, and thus s2 will be available after four gate delays. It is very important to see that all these things are are actually occurring parallelly. Okay, because all these inputs are available at t equals to 0, so all these P3, G3, P2, G2, P1, G1, P0, G0 all will be available after single gate delay. Okay, I'm just assuming that the delay of XOR and AND are same. Okay, just I'm taking a single gate delay, that's why. Otherwise, the gate having more delay will dominate. Okay, so these things are taking place parallelly. That's why after single gate delays, all these are available. After two gate delays, all the carries are available, and after one more gate delay, all the output sum are available. So total four gate delays are needed in this whole circuit, which is much less than the ripple carry adder. But the very important thing is that, as we know that here we will need more number of gates. Okay, more number of gates are needed here. Okay, so it is very clear. Look ahead carry adder, very important point is that only four gate delays are needed. The things, all the circuit is working parallelly, that's why four gate delays are needed. Okay, in the ripple carry adder the things were working sequentially, here the things are working parallelly, that's why more circuitry is needed. Very important point, only four gate delays are needed here. Okay, okay, so let us do one example here. Suppose it is given that XOR gate has a delay of 10 nanoseconds, AND gate has a delay of 20 nanoseconds, and OR gate has a delay of 10 nanoseconds. Okay, so we have to find the total delay in the carry look ahead adder. Okay, so we have to find the delay here. Okay, so let's solve the question. Okay, so this is given that XOR has a delay of 10 and AND gate has a delay of 20. Okay, so 10, 20, 10, 20, 10. So all the inputs are available at t equals to 0. Okay, all this pi will be available at 10, gi will be available at 20, 10, 20, 10, 20, 10, 20. Okay, now let's move on to the back circuit. Okay, this one. As we know that these PIs are available at 10, GI are available at 20. So the input to this whole circuit is available at 20 nanoseconds. Okay, the correct input. Okay, the actual input. Now again, this OR AND gates are in level 1, so they will take 20 nanosecond delay, and OR gate, I think I have taken OR gate delay as 10 nanoseconds, so they will take 10 nanoseconds. So these carry outputs will be available after 20 nanosecond delay plus 10 nanosecond delay, that is 30 nanosecond delay. Now since the input was available to the circuit at 20 nanoseconds, the delay of 30 nanoseconds will give us the output of carry at 50 nanoseconds only. Okay, so the carry output C0 is already available, C1, C2, C3, C4 and all the carries will be available at 50 nanoseconds and not before that. Okay, so the carry outputs will be available at 50 nanoseconds. Okay, and these sum, since there's XOR gate, so they will take 10 nanoseconds more and they are also working parallelly. So the output will be available at 60 nanoseconds. The correct output will be available at 60 nanoseconds. Okay, so that is a solution to this problem. Such kind of problems are generally asked in GATE exams. So now let's move on to the 2's complement addition and subtraction problem. So now let's look at the 2's complement addition and subtraction of two 4-bit numbers. Now first of all, let's look at what is 2's complement. Okay, now in digital format, the negative numbers are actually represented by 1's complement format and 2's complement format. Okay, so now let's first of all analyze or look at the 2's complement format. So for example, if we have 4-bit numbers, okay, the first bit, the MSB of any number, so if any number is written is in 2's complement, 4-bit number in 2's complement, so the MSB is the sign bit, okay, is the sign bit, and the rest of the bits, rest of the bit decide the magnitude. Okay, rest of the bits decide the magnitude. Okay, so whenever MSB is 0, that is the sign bit is 0, then the number is positive. So sign bit is 0 means number is positive. Okay, and obviously the rest of the bits, for example, I am taking 4-bit numbers, so 000 means it is plus 0 because magnitude is 0. 0 it is plus 1 because magnitude is 1. 0 similarly all the numbers 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1. So we have plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7. Okay, so whenever MSB, that is the sign bit, is 0, then the rest of the bits show the magnitude. Okay, so the number will be plus the magnitude. Okay, so it will be a positive number and magnitude can easily be obtained from the rest of the bits. But whenever we have to write -1, okay, so I have to write -1 here. Okay, so how to write any negative number? How to write any negative number? How to write any negative number? So it's very simple. So first of all, write the positive number. First of all, write the positive number. Then complement it. Complement it. That is, once 1 will be replaced by 0 and 0 will be replaced by 1. complement it, and then add 1 to it. Okay, add 1 to it. For example, plus 1 is the sign bit, 0 0 1. Okay, so minus 1 will be, so first of all we'll complement it. Okay, so it will be 1 1 1 0, and then we will add 1, so 1 1 1 and 1. Okay, so this is your minus 1. Plus 2 is 0 0 1 0. Minus 2 will be complemented 1 1 0 1 and then add 1. So when we'll add 1, so it will be 1 1 1 0. Okay, so this is the sign bit. Okay, this is the, so this is number. So this is the sign bit, and sign bit is 1 means it is a negative number. Similarly, plus 3 is 0 0 1 1. So minus 3 will be, first of all complemented 1 1 0 0 and then add 1 1 1 0 1. So this is the sign bit. Plus 4 0 1 0 0 complemented minus 4 4. So first of all we will complement it 1 1, sorry, 1 0 1 1, and then we will add 1. Okay, so we'll get 1 1 0 0. So this is the sign bit. Okay, similarly we can get all. So minus 5, sorry, plus 5 is 0 1 0 1, minus 5 complemented 1 0 1 0, and then add 1 1 0 1 1. This is the sign bit. Okay, similarly we can write plus 6. So plus 6 we know 0 1 1 0. So minus 6, first of all complemented 1 0 0 1 and then add 1, so it is 1 0 1 0. Okay, so similarly we can write plus 7 is 0 1 1 1, minus 7 complemented 1 0 0 0. So 1 0 0 1 will be the 2's complement, and this is the sign bit. Okay, now if we, okay, just I'm just adding an image here. Okay, so this will represent all the positive and negative numbers for 4 bits. Now if we see that we have written plus 7, all these we have written, there is no minus 0 in, okay, there is no minus 0 representation in 2's complement. Okay, now if we see that, we will see that there are 8 numbers here and there are 7 numbers here, but one code of 4 bit, that is 1000, is not used anywhere. So in 2's complement format, 1000 is assigned to minus 8. Okay, so a number in 2's complement I'm just writing the conclusion. If the MSB, that is sign bit, is 0, then number is positive and the rest of the bits, that is the bits leaving the sign bit, represent the magnitude of the number. Okay, if the number is negative, that is sign bit is 1, then to find out its magnitude, okay, so to find out this magnitude, first of all complement the number, okay, and add 1 to it to get its magnitude. Okay, so to get its magnitude, for example, if somewhere it is written that it is 1100, okay, so obviously it is a negative number. Now how to know that what is the magnitude of it? So first of all, complement it, so we will get 0011 and then add 1 to it, okay, so it will become 0100. So we will get that it was a negative number and we'll get that the magnitude is 4. Okay, so we can see that it is correct. This method is applicable for this also. For example, it is given that 1000 is a number. So obviously since sign bit is 1, so it is a negative number. To find out its magnitude, we will first of all complement it. We will get 0111 and then we will add 1 to it. So we will get 1000, the magnitude. Okay, so the magnitude is 8 and the number is negative. Okay, so this method will work here also. Now we have seen 2's complement. Okay, so I think I will need more pages here. So we have seen 2's complement. Now we will see addition and subtraction of the two numbers written in 2's complement format. Okay, so we have a simple 4-bit adder. Okay, simple 4-bit adder. Okay, so these are the two values, S0, S1, S2, S3. Cout is the output, and we can apply an input carry also if needed. So two inputs, that is A3, A2, A1, A0, B3, B2, B1, B0. Okay. Now since the inputs are in 2's complement, there are 4-bit inputs. So obviously these inputs. So this is the sign bit. Okay. A3 is a sign bit. Similarly, B3 is also a sign bit. Okay. A3 and B3 are the sign bits. Okay. Now first of all, I will see that how to perform addition. Okay, how to perform addition. First of all, let's look at, so we have to add two numbers. Okay, so for example, just I'm taking an example. For example, let's add 7 with -4. Okay, so A is 7 and B is -4. So A is equals to sign bit, it is a positive number and it is 7, and B, it is a negative number, and we know that -4 is written as 1100. 1100. Now we will simply add these two numbers. Okay, so this is 7, this is -4. We will add these two numbers. So what we will get? Okay, now we know that since this 4-bit adder simply add the two numbers, and we are assuming that here Cin is 0. Cin right now is 0. Cin is 0. So we'll add these two. So 1, we'll get 1 here, we'll get 0 here, and we'll get 1 carry here, we'll get 0 here, and 1 carry out also. Okay, so this is the sum output, that is S, and this is the carry output, that is, this is C out, and this is your sum S. Now we can see that 7 minus 4 is 3 only, and we are getting sum, that is 3, but we are getting a carry output, that is 1. So sum is 0011. Okay, since the inputs were in 2's complement format, the output will also be in 2's complement format. So this is the sum has the MSB equals to 0, that is the sign bit of the output is 0, so the output is positive, the magnitude is 3, and the carry bit C out is neglected. Okay, C out is neglected. Is it okay? Now let's look at another example. Okay, so let's add the two numbers 7 plus 7. Okay, so we have two numbers, A is also 7, B is also 7. Okay, so A is equals to 0 1 1 1, B is equals to 0 1 1 1. So 0 1 carry, we'll get 1 here, 1 carry, we'll get 1 here, 1 carry, we'll get 1 here, and 0 here. Okay, so this is the carry output, this is KC out, and this is your sum S. Okay, now we will analyze this first, but first of all let's look at the examples first. Okay, let me not waste page here, just for simplicity I'm just writing it again. 1 0 0. Okay, so we got this as C out and this as sum. Then we solve plus 7 plus 7. We got 0 1 1 1 0. This has C out, this has sum. Now let's solve for minus 4 and minus 5. Okay, so we have 1 1 0 0, and let's see what is minus 5. So minus 5 is 1 0 1 1. So it is 1 1 1 0 1. So this is C out and this is your sum. Okay, now let's solve one more. Okay, let's solve one more. Let's take plus 3 and minus 6. So plus 3 0 0 1 1, and minus 6, let us see what is minus 6. Minus 6 is 1 0 1 0 1 0 1 0. Okay, so carry out is 0. This is your sum. Okay, now if we will analyze, we can see that this case 1 and this case 4. Okay, so in case 1 and case 4, A and B. Okay, in case 1, in 1 and 4, input A and B were of different sign. Okay, they were of different sign. So in those cases, carry output is neglected. Carry output is neglected, and the sum act as the actual result. Okay, so this we will neglect this and we will keep this as the result. Now here the result is this 0 0 1 1 with this as a sign bit and this as a magnitude bit. Similarly, here we will keep this 1 1 0 1 and we will neglect this. So this will act as a sign bit, and 1 0 1 will give us the magnitude. Okay, so we can see that 1 1 0 1. So if we compare 1 1 0 1, we will see that 1 1 0 1 is minus 3. So that is correct. Okay, so this is very important. that whenever A and B are of same signs, are of different sign, then then carry out is neglected and the sum act as an actual result. The MSB of the sum will act as a sign bit and the rest will give us the desired magnitude. But in case 2 and 3, A and B were of same sign. Okay, so in this case here we will not neglect the carry out, okay, rather see out with sum, okay, see out with sum act as the result, where see out act as a sign bit and the sum give us the magnitude of the number. For example, here plus 7 plus 7, when we add these two, so this is the result where C out is not neglected, rather this will act as a sign bit and this will give us the magnitude. Okay, similarly when we take input as -4 and -5, okay, so this one and the C out will act as a sign bit showing that it is a negative number and this will give us the magnitude. So 10111 is the result. Okay, now how to get the magnitude of this? We know that we will first of all complement it, then we will add 1 and then we'll get the result. Okay, so this is very important conclusion that I wanted to tell you. Okay. Okay, so in case of addition, when the two numbers are of different sign, we just remove or carry out is neglected and the sum act as the actual result. When A and B are of the same sign, then we will not neglect the C out, rather C out with sum act as a result, with C out giving us the sign bit of the result. Okay, now so now let's look at how to subtract the two numbers. Suppose two numbers are given to us. Okay, so we have to perform subtraction, that is A minus B using the adder. Okay, so we do not have any subtractor. We have a 4-bit adder and we have to use it as a subtractor. Okay, now first of all, how we will do it? Okay, so subtraction means, okay, A plus minus B. Okay, so we can see that it is converting B into a negative number. Okay, converting B into a negative number and then adding it with A. Okay, so that is equivalent to, so we will add A with negative B. Okay, negative B. So for example, if I want to add 4 7 sorry, if I want to subtract 7 minus 4 is to be performed, then we can say that it is 7 plus 2's complement form of 4. Is it okay? Okay, because 2's complement form of 4 is equals to -4. So when we are adding with 7, it is actually we are performing 7 minus 4 only. So we will add A with negative B. So it is equivalent to, so how to get negative B? Negative B means 2's complement of B. 2's complement of B. And how to get 2's complement of B? 2's complement of B is equal to complement of B plus 1. Okay, we know that. Just invert all the terms of B and then add 1. Okay, so if we want to use the same adder, 4-bit adder with input A4, A3, A2, A1, A0. Now the input will be connected, since we want to use it as a subtractor, so we will put a NOT gate here. B3, B2, B1, B0. The output sum S3, S2, S1, S0, Cout, and this is Cin. Now whenever we will perform subtraction, we will put Cin is equals to 1, because in this case we are performing A plus B complement plus 1. Okay, because Cin is equals to 1. That is equivalent to, since B complement plus 1 is 2's complement of B, so it is equivalent to A plus 2's complement of B, that is equal to A minus B in the digital format. Is it clear? Now, we will use the relationship that we have seen there, that in addition we have seen that when we were performing A plus B, then if A and B were of same sign, then result is Cout with some bit, where Cout act as a sign bit and some bit act as a magnitude. And if A and B were of different sign, then the result is, and in this addition case we put Cin is equals to 0. Result is, we just neglect the Cout and result is only sum. Okay, the MSB of sum was the sign. Exactly similar but opposite result will be in the subtraction. So when we are performing A minus B, if A and B are of different sign, then the result is Cout put with sum, where Cout is sign and sum is the magnitude. Sum will give us the magnitude. So if sign bit is negative or sign bit is 1, then we know how to find the magnitude. Okay, and if A and B are of same sign, then result is only the sum, Cout is neglected, and the MSB of sum will give us the sign of the result. Okay, so exactly similar but different results, but this is very important. Okay, now how to perform subtraction using adder? So this is the method how we will do it. Okay, so we have a serial adder. So in the serial adder we are using registers. So how a register works, let us see a very brief introduction to registers. We will see them in the very good analysis later on. So let us see a register. What is a register? So suppose this is a register which has stored values. Stored values are A0, A1, A2, A3 and so on. So with the clock, the input inside the register will shift to the right. Okay. So in the first clock of the tick, okay, tick of the clock, output will be A0, second tick output will be A1, third tick output will be A2, fourth tick A3, fifth tick A4 and so on. Similarly for the this register also. And in this register, okay, this register, if you look at the sum register, okay, it will be initially empty because this is producing the result. Okay, so this will be initially empty. So in the first tick of the clock, S0 will be stored here. In the second tick, S0 will shift to the right, and this space will become empty. The first space will become empty. So this will be S0, and here S1 will get stored. In the next tick, both will shift to the right, and this is S1, S0, and there will be S2, and so on. Okay, and in this register, this is a single flip flop. Okay, so it's a single bit register, we can say. So it is storing this C output, and in the next tick of the clock, it is producing the same C output at the input. Okay, now how it is working, let us see. Let us see the analysis. Okay, so I'm just reducing the size. Okay, so initially this flip flop was clear. There was nothing at the output. Okay, now in the first tick of the clock, A0 will be present here, B0 will be present here, and since flip flop is initially cleared, so here output is 0. So will get S0, that is A0 XOR B0. We will get C output, that is this is the full adder. So it will produce the output corresponding to A0, B0, and 0. So it will be A0 into B0, because this C in initially is 0. So we will get C0, so we'll get C1 here. So this is C1. Okay. Now if I draw the clock, so at the tick of the clock, A0 and B0 will present here. The full adder do the computation. S0 is present here, and C1 is present here. Now at this tick of the clock, this C1 is produced at the output with the help of this flip flop. This S0 is stored into the register, and this register remove this A0 and B0 from the output and start producing A1 and B1 at the output. Okay, so in this tick of the clock, A1 and B1 are produced at the output of these registers. S0 is stored into the register. C1 is produced in the input of the full adder. Okay, so if I see the scenario, then it will be okay. So if I see, it is A1, B1, C1. Okay, now the full adder. So after this clock, the full adder start working, and full adder produce the output, that is S1, that is equals to A1 XOR B1 XOR C1, and C output is produced, that is C2. Okay, now again the clock will come, and at this tick of the clock, S1 value is stored into the register, and this register shift to the right. A1, B1 are cancelled, and this register start producing A2, B2, and this C2 is moved from output to input with the help of this flip flop at this tick of the clock. So here we have A2, B2, and C2 as an input to the full adder, and thus the full adder start working with these inputs. So here we have A2, B2, and C2. So we will get S3 and C3 at the output. Okay, so they will get stored here. So we'll get S3, no, S2. So that's the simple thing. S2 and C3. So S2 will be produced and so on. The things will work like this. So with every clock, with every clock, this register will keep on shifting, and these register will also keep on shifting, and slowly we will get all the result stored. The final result will be stored in this register, the output sum register, and the final last C out, the carry output bit will be produced here. Okay, so it will work like this. Okay, so if there are n bits in the input, we will need n clocks for the to get the output. Clear? Now a very basic question that can be asked in this circuit is that what should be the minimum clock frequency? Okay, what should be the minimum clock frequency? Now let us see how this circuit is working again. So let us say that at this tick of the clock, here A2 and B2 are present, and here C2 is present. Okay, so A2, B2 and C2 are present. Now obviously this full adder will take some time to produce the output sum and to produce the output carry. Okay, so to produce the output carry, that is C3, and the sum, that is S2. Now at the next tick of the clock, we know that the input will be A3, B3 and C3. Okay, now if the time period of this clock is less than the time period taken by this full adder to produce the output sum, that is S2, then if this clock comes before the full adder is able to make the output sum S2, then obviously this output sum S2 will get corrupted. Is it okay? So it is very clear, and also it is also very important to see that this output C3 should also be available from the full adder before this clock comes. Okay, so in this time period, that is in one time period of the clock, the output sum S2 and C3 should be available from the full adder. Okay, so from the full adder, S2 and C3 should be available at the outputs. Otherwise, if the clock comes before these outputs are available, then the next outputs will be corrupted. Okay, so it is very clear that time period of the clock should be greater than time taken by the full adder to produce the sum, and time of the clock should be greater than the time period taken by the full adder to produce a carry. So we can say that time period of the clock should be greater than the maximum of the sum and carry. Okay, so this is very important. This kind of question can be asked in GATE, and we have analyzed the serial adder also. It's a very simple kind of circuit. Okay, so thank you students. We have analyzed 4 very basic and very good combinational logic circuits. So thank you.